Welcome back to AI Paper Podcasts. Today, we're diving into something really fascinating, a major challenge for AI models, getting them to properly understand really long videos.
Yeah, not just short clips. We're talking minutes, maybe even hours of content.
Exactly. It's like imagine asking an AI to give you a good summary of a whole movie when it's only seen a couple of screenshots. It's just a different ballgame entirely.
It really is. This goes way beyond just spotting objects in a frame.
Yeah.
It needs complex reasoning, something current vision language models, VLMs, have, well, frankly struggled with.
Which is why we're focusing today on a really important new paper. It's called Scaling RL to Long Videos. It comes from a team up between NVIDIA, MIT, HKU, and UC Berkeley.
Right.
And they've developed this whole framework, Long-Villa R1, that seems to be pushing the envelope quite a bit for what VLMs can actually do with long video. If you're into AI research, especially vision or NLP, this is one you'll want to know about.
Definitely. So for maybe a quick 1 minute rundown for everything.
Yeah, let's do the short version.
Okay, so big picture. VLMs have been hitting a wall with long videos. Two main reasons. Not enough good, diverse training data for this kind of reasoning.
Right.
And just the sheer computational cost. Training, especially with reinforcement learning, gets incredibly expensive and tricky.
So this paper tackles both head on.
Exactly. Their solution, Long-Villa R1, has sort of three key parts. First, a brand new data set they built called Long Video Reason.
Okay.
Massive, 52,000 question-answer pairs, designed specifically for complex reasoning. Think sports, games, vlogs, really diverse stuff.
And what's the second part?
A two-stage training pipeline. It combines chain-of-thought supervised fine-tuning CoT-SFT with reinforcement learning, basically teaching the model how to reason step by step.
Makes sense. And the third?
This is clever. It's an infrastructure improvement called the Multi-modal Reinforcement Sequence Parallelism, or MRSP.
MRSP, okay.
This thing drastically speeds up the RL training, like up to 2.1 times faster for long videos, and crucially, it stops those out-of-memory errors that used to plague this kind of work.
So the impact?
Pretty huge.
Yeah.
Their Long-Villa R17B model hits state-of-the-art. It beats other open-source models and actually matches giants, like Gemini 1.5 Pro, on these tough reasoning tasks.
Wow.
And it gets better as the videos get longer. It's a really significant step towards AI that can actually follow, a whole visual story.
Okay, that's a fantastic summary. So let's unpack that complexity a bit more. Why is understanding long videos so much harder than short clips or images? It feels like more data should just work better, but obviously not.
Yeah, it's not that simple at all. It demands reasoning across, well, multiple connected dimensions. First off, there's temporal reasoning.
Temporal, like over time.
Exactly.
Right.
Integrating clues and events that happen over duration. Think about, say, predicting who wins a football penalty shootout.
Okay.
It's not just the last kick. You need to pick up on emotional cues, player fatigue, maybe tactical shifts during the whole extra time leading up to it.
Right, connecting the dots across the timeline. That's very different from just recognizing, oh, someone kicked a ball.
Precisely. Then you have spatial reasoning.
Spatial tracking things?
Yeah, accurately tracking entities as they move, like those shell games, hiding a ball under a cup, swapping them really fast.
Oh yeah, I'm terrible at those.
And most people are.
Yeah.
For an AI, figuring out the ball's final spot after lots of quick, precise swaps needs really deep spatial understanding, not just identifying cup.
Okay, that makes sense. Temporal, spatial. What else?
Then there's goal-oriented reasoning. This is about inferring sort of hidden goals or strategies.
Well, like in poker.
Perfect example. Interpreting a player's bet beyond just the action itself. Are they bluffing? What's their likely hand? What are they really trying to achieve with that move?
Okay. And the last one?
Narrative or plot reasoning. Understanding how storylines evolve, how characters develop, the overall flow of events over a long time. This is often where AI gets lost in longer videos, right?
Yeah.
It sees the trees but misses the whole forest.
Yeah, definitely. And you mentioned data scarcity earlier. That seems like a huge bottleneck, too.
Oh, it's massive. Collecting really good annotated long video data for reasoning is incredibly hard.
Yeah.
It's not like math problems or code where the structure is clear.
Right.
For video, you need to annotate complex timing, goals, spatial stuff, narrative arcs, sometimes over hours of footage. It's super labor intensive, can be subjective, and just doesn't scale easily. That's really held back VLM progress in this area.
And then even if you get the data, the training itself is a monster.
Yeah.
What makes the training, especially using RL, so difficult for these long sequences?
It really boils down to the sheer volume of information from all those frames. Long videos create these enormous visual embeddings, which means you need huge amounts of memory.
Yeah.
And the rollout times in RL where the model generates potential answers become incredibly long.
This memory and time.
Yeah, those two combined just make it almost impossible to train effective long video VLMs with strong reasoning using the older RL frameworks. They just weren't built for that kind of scale. You run out of memory, things take forever.
Right. So enter long video R1 and its three-part strategy. Let's dig in at that first part. The long video reason dataset. How big did you say it was, and what's the special sauce?
It's pretty big, 52,000 question-answer pairs from over 18,000 different videos. Covers sports, games, vlogs, good variety.
Okay.
But the key thing, the special sauce as you put it, is that it's high quality and uses chain of thought, CoT annotation.
Right, the CoT. Why is that so vital?
Because it teaches the model how to arrive at the answer, not just what the answer is. It provides that kind of reasoning roadmap.
That how seems absolutely crucial for building real understanding, not just pattern matching. So how did they actually create this data set? You mentioned curation magic.
Yeah, they used a pretty smart automated pipeline, actually leveraging other AI models. First, they chopped the raw videos into smaller, like 10-second clips.
Okay.
Then they use a powerful VLM, NDLA 8B, to generate captions describing what's happening in each clip.
Got it. So descriptions for each short piece.
Exactly. Then they take a strong open source reasoning LLM. They feed it all the captions from a single video.
The whole sequence of captions.
Right. And they prompt this LLM to generate question reasoning answer pairs that force it to reason across multiple clips, across the whole video's content.
Ah, so the prompts guide it to ask questions needing that temporal or spatial or goal-oriented thinking across the entire video duration. Clever.
Very clever. They actually designed 4 specific prompt types to push the LLM towards each of those reasoning categories: temporal, goal purpose, spatial, and plot narrative.
Okay.
And to make sure the VLM really focuses on the visuals, not just the text captions, they put phrases in the prompts like checking the video or analyzing the scene, kind of nudging it to look closer.
Nice touch.
Then another LLM cleans up the reasoning steps. And importantly, for reliable testing, they also hand-curated a benchmark set 1,000 really good, complex reasoning questions across the categories. They call it Long Video Reason Evil.
That sounds incredibly thorough. And what about that filtering strategy? Classifying questions as easy, hard, medium. Why do that?
That's all about optimizing the 2 training stages. The easy and hard questions are mostly used for stage 1, the CoT-SFT. This helps get the model started, basic reasoning, following the instructions for long videos.
Right, build the foundation.
Exactly. But the medium samples, the ones where the initial model wasn't quite sure, giving diverse answers, those are saved for stage 2, the RL training.
Why reserve those specifically for RL?
Because the RL algorithm they use, GRPO, works best when the different attempts or rollouts for a given question are varied. It needs that diversity to learn effectively. If all the questions are too easy or too hard, the learning signal, the gradient, can just disappear.
Ah, okay. So the medium ones provide the best learning signal for RL.
Precisely. And they also threw in about 110,000 extra video samples from other open source data sets into that RL mix just to help it generalize better.
Okay, that makes perfect sense. And it leads us right into that 2-stage training pipeline. Stage 1, long CoT-SFT. What's the main goal there?
Stage 1, the supervised fine-tuning, is really about initialization, giving the model that core ability to reason and follow instructions, specifically tuned for long video inputs.
Using those 18,000 high-quality CoT samples from their data set.
Right. And they actually use an efficient system called MMSP from the original long video work to handle the SOT efficiently, even with hundreds of frames. So it's about laying down a solid foundation.
A strong base. And then stage 2 builds on that with reinforcement learning, which is known for getting models to hit really specific complex goals.
Exactly right. Stage 2 uses an RL algorithm called GRPO, Generative Reinforcement Policy Optimization.
GRPO.
Yeah. It basically lets the model learn through trial and error, refining its reasoning based on rewards it gets for accuracy and getting the output format right. The goal here is to really scale up those reasoning skills.
Pushing it further.
Yeah, guiding it to explore different reasoning paths and figure out more effective, more general strategies. And this stage uses those 33,000 tricky medium samples from their data set, plus the extra 110,000 external ones, really pushing the envelope.
And fundamentally, GRPO is solving that alignment problem, right? Making sure the model doesn't just give an answer, but reasons towards the right kind of answer.
That's the core idea. But as we discussed, even with a good algorithm like GRPO, doing RL on long videos was computationally brutal. Which brings us to their third big innovation, MRSP.
Multi-modal reinforcement sequence parallelism, the efficiency engine you called it.
Right.
What was the specific bottleneck in older RL setups that MRSP fixes?
So existing RL frameworks for VLMs just choked on long videos. You have this huge number of tokens from all the frames,
Right.
which demands massive amounts of memory to store features. Plus, the computation needed during the rollout phase generating answers and the pre-filling phase processing the input was just immense. MRSP was built specifically to break through those bottlenecks for RL on long video.
So how does it work? Let's start with stage 1 of MRSP, the rollout part, with parallel encoding.
Okay, so instead of one GPU trying to process the whole video, they split the input frames evenly across multiple GPUs.
Okay, divide and conquer.
Exactly. Each GPU processes only its slice of the video frames using its own vision encoder. Then, the resulting video embeddings, along with text embeddings, are gathered together using an all-gather operation.
So everyone shares their piece.
Right, so the whole model gets the complete picture. This spreads out the work and crucially avoids running out of memory on any single GPU. And here's a key optimization. Those gathered embeddings are then cached.
Cached.
Yeah, stored temporarily. And they're reused for multiple rollouts, maybe 8 to 16, within the same training step. This avoids recalculating the same visual features over and over again, saving a ton of time.
That caching sounds like a huge win. Okay, so that speeds up encoding and rollouts. What about stage 2 of MRSP, the pre-filling part, with sequence parallelism? How is that made efficient?
Right, so for every rollout attempt, both the main model, policy, and a reference model need to do this compute-heavy pre-filling step, especially with the huge number of tokens and long videos.
Okay.
Since the embeddings are already gathered, cached, and reused from stage 1, MRSP parallelizes this inference step 2. The input embeddings are padded, so they're all the same length.
We set the work.
Yep. And then they're partitioned across the GPUs again. Each GPU calculates the logits, basically the raw scores for the next word token, just for its assigned slice of the sequence working in parallel.
So they parallelize the most calculation-heavy part of the RL loop.
That's exactly it. It's a really smart way to distribute the computation.
And what was the real-world impact? Did this MRSP system deliver on speed and efficiency?
Oh, definitely. They saw up to a 2.1x speedup for RL training on 512 frame videos with 7 billion parameter models compared to older methods.
Wow, more than double the speed.
Yeah. And maybe even more importantly, it eliminates those GPU out-of-memory errors. This let them train on much longer sequences, up to N of 1024 frames.
So bigger models, longer videos.
Exactly. They showed they could do RL training on hour-long videos that's like 3,600 frames, maybe 256,000 tokens, using just a single A100 node, which has 8 GPUs. That scale was just not feasible for RL.
That really is a breakthrough, and they're releasing this system.
They are. It's publicly available, supports different types of input like video, text, audio, works with various models. It's a big contribution back to the research community.
Fantastic. Okay, so we have this impressive framework, great data set, smart training, efficient system. Let's talk results. How did Longville R1 actually perform against other top models?
On the standard video benchmarks, the Longvilla R17B model consistently did better than its counterpart that didn't have the RL training, Longvilla 7B, across 9 different benchmarks.
So the RL stage definitely added value.
Clearly. For instance, it hit 68.4% on video ME using subtitles, which was among the leading scores, showing strong performance across different video lengths.
But the real acid test was their own long video reason evil benchmark, the one designed for that deep reasoning. How did it do there?
That's where it really shone. Longvilla R17B got an average accuracy of 67.9% across those 4 tough reasoning categories: temporal, goal, spatial, plot.
And how does that compare?
Significantly better than other open source models like Video R17B, which was at 62.7%. It even edged out proprietary models like GPT-4o, which scored 60.7%.
Better than GPT-4o on this task.
On this specific benchmark, yes. And incredibly, it essentially matched Gemini 1.5 Pro. Gemini got 67.3%, Longvilla R1 got 67.9%, and Longvilla R1 was particularly strong on spatial reasoning, hitting 70%.
Matching Gemini 1.5 Pro is seriously impressive. That really shows the power of this approach for complex reasoning.
It really does. It's a genuine leap forward.
And you mentioned earlier it gets better with longer videos. It scales well.
Yes, that was another key finding. They tested a smaller 1.5B parameter version, Longvilla R1 1.5B. As they fed it more frames, its performance kept improving, reaching 64.3% accuracy at 512 frames. It was clearly integrating information from the longer sequence.
Unlike the baseline.
Right. The baseline model without RL actually peaked earlier, at 256 frames, and its performance dropped when given 512 frames. It just couldn't handle that much information effectively. So Longville R1 is genuinely built to understand longer narratives.
Okay, let's make this concrete with those real-world examples they showed. The moving cup and ball game, the spatial tracking one, how did Longville R1 handle that?
It nailed it. It precisely tracked the cups through all the swaps to figure out where the ball ended up. This requires constant spatial awareness, remembering where things were and how they moved.
And other models struggled.
Yeah, they mentioned Video R1 just couldn't deduce it accurately, and even Gemini 1.5 Pro's reasoning was apparently a bit shaky or inconsistent on that one. Longvilla R1 showed superior tracking.
Okay. What about the football penalty shootout prediction? That seems like a mix of temporal and goal reasoning.
That was impressive too. After watching 30 minutes of extra time, Longvilla R1 integrated all sorts of clues player performance earlier in the game, their apparent emotional state, key saves by the goalie to make an accurate prediction.
It understood the context, the flow.
Exactly. They contrasted this with Gemini 1.5 Pro, which apparently made some factual errors in its reasoning, and Video R1, which gave a much less detailed summary. Longvilla R1 seemed to grasp the game's narrative arc.
And the last one, the detector game, finding the subtle clue.
Right, Susan realizes the man isn't her husband. Why? Longvilla R1 correctly identified the crucial visual detail. The man wasn't wearing a wedding ring on his left hand.
Ah, a very specific small detail.
Exactly. It shows the model can focus on tiny but critical visual elements that are key to understanding the plot, even when other models might miss them or get sidetracked. It's that combination of detailed visual perception and narrative reasoning.
So, wrapping this up, it really feels like Longvilla R1 isn't just an incremental improvement. It's a significant step towards VLMs that can genuinely process and reason about the complexities found in long-form video.
I think that's fair to say. It tackles the core problems, data, training complexity, efficiency, head-on, with a full-stack solution.
And the potential applications seem huge. You think about robotics.
Absolutely. Embodied AI agents that can understand long sequences of events, track objects over time, figure out cause and effect for complex tasks. That's a game changer for robotics.
Or things like autonomous driving, AR, VR, needing that deep, dynamic understanding of the environment.
Definitely. Or even think about practical tools, AI tutors that can summarize hours of lectures intelligently, systems helping doctors review long procedural videos for critical moments.
Sports analytics could get incredibly deep, understanding the strategy and momentum shifts across an entire game, not just isolated stats.
Yeah, the ability to grasp that narrative flow is key.
So it makes you wonder, as these models get capable of handling hour-long videos, maybe even denser visual information, what kinds of completely new AI applications might pop up? Things we haven't even thought of yet.
That's the exciting question, isn't it? Maybe in creative fields, AI assisting with plot development by understanding long character arcs, or in science, analyzing hours of experimental footage to find subtle patterns.
And what does this mean for our understanding of AI memory? What are the next big questions we need to ask about long-term visual memory, about continuous learning from video streams?
Exactly. This work opens up those questions. We've made a big leap in processing long videos, but understanding true human-like comprehension of visual narratives.
Yeah.
Well, that journey's really just getting started.